Why don't we get started here? Good afternoon. It says here I'm Alec Gelmer, Robert J. Vlasic, Dean of Engineering, so I guess that's got to be accurate. Thank you for coming here today. As you know, endowed professorships are among the highest honors presented by the college. They enable us to acknowledge faculty contributions in research, teaching, and service. Funded and named by our donors, these gifts are instrumental in helping us attract, reward, and retain outstanding faculty members. Here we honor Dr. Krishnan Mahesh as the Richard B. Couch Professor of Naval Architecture and Marine Engineering. Congratulations. This endowed professorship was established by two-time Michigan engineering graduate and longtime NAMI Advisory Board member John C. Couch in honor of his late father, Richard B. Couch. John also provided the gift to name the Couch Carriage in the Aaron Friedman Marine Hydrodynamics Laboratory, further honoring his father's legacy. Richard B. Couch joined the university as Professor of Naval Architecture and Marine Engineering and Chairman of the Department of Naval Architecture and Marine Engineering in 1957. Previously serving as Chief Naval Architect with the U.S. Navy Department's Bureau of Ships, Richard brought with him ambitious plans for improving the scope of educational programs and the capabilities of the model basin. His arrival, of course, coincided with the Soviet Union's Sputnik launch, Sputnik 1, and the subsequent renewal of national interest in science and engineering. As such, Richard put a strong emphasis on graduate education and persuaded the college to invest heavily in NAMI's laboratory facilities at the Marine Hydrodynamics Lab. Over his 10-year tenure as chair of the department, more than doubled the size of the faculty and student enrollment and initiated a viable doctoral program. Richard's career with the Navy began after graduating from the Webb Institute of Naval Architecture in 1933 and his graduate study at the New York University the following year. He continued to serve the U.S. Navy Department and the Department of Defense in various capacities after coming to the university. Richard was a member of the American Society of Naval Engineers and the Royal Institution of Naval Architects. And he was designated the David Taylor Medalist by the Society of Naval Architects and Marine Engineers in 1966, which is the highest award this professional society confers for technical achievement. It is fitting that the professorship bearing his name is being presented today to another distinguished leader in the field. Again, congratulations to Richard B. Couch, Professor of Naval Architecture and Marine Engineering, Dr. Krishnan Mahesh. I would now like to invite Department Chair David Dowling to the podium to introduce our next speaker.
Okay, I'm pleased to introduce Suman Mupidi. He is Professor Mahesh's first PhD student and was a longtime member of his research group at the University of Minnesota. He is an aerospace engineer at the NASA Ames Research Center. At Ames, Suman has contributed to various efforts, including Venus exploration, mission proposals, commercial spaceflight partnerships, the Orion spacecraft post-flight characterization, and high-altitude rocket launch parachute test demonstrations. Suman currently leads the team responsible for aerothermodynamics and thermal protection system for NASA's next flagship class mission to Mars, the Mars Sample Retrieval Lander. So, let's get him set up.
Yes, good.
Professor Mahesh, Dean, faculty members, students, and guests, thank you for having me here. It gives me great pleasure to be able to talk about my advisor, Professor Krishnan Mahesh, at this milestone event and as part of this ceremony. Mahesh, congratulations. I really wish I was attending this in person, but thanks to Jasmine for allowing this video message. My association with Professor Mahesh begins in the fall of 2000. I was a first semester graduate student at the University of Minnesota, Mahesh had just joined as faculty, and it was announced that he was looking for graduate students. I emailed him, we had a short conversation. I admitted that I had very little programming and CFD experience, but I still would like to work with him. A day later, he emailed saying he would be my advisor, and he recommended a Fortran 95 textbook to purchase. I still have that book. I needed it. I was Mahesh's first student and his only student for a while. We met almost every day. He was very involved in the grid generation, coding, debugging, hands on research. In time, the research group grew to be near 10 students and maybe 2 or 3 postdocs, but he always made time to meet all of the group members regularly. It was an unusual week if we did not see him drop by our offices 3 times a week. By example, he showed us that he cared about the work we did, that he prioritized his interactions with us despite everything else that was on his schedule. And he showed that mentoring us was a big part of his job and his schedule. Also, by example, Mahesh showed us that any job one does should be done with the fullest of an effort and attention. As an example, I chose that in 2009, Mahesh volunteered to help convene the annual division of the Fluid Dynamics Conference in Minneapolis. And he was involved with almost every part of this planning and organization: website, finances, selection of the venues, reviewing of the abstracts, scheduling the keynote presentations, all the way to standing at the reception dinner during the conference along with us volunteers, making sure that the attendees and the guests were comfortable and they were well taken care of. It was a year-long effort. No detail was too small, and by all measures, this conference was a great success. Watching him, we learned a lot. As another example, I want to show that Mahesh took his role as a teacher very seriously. He taught various undergraduate and graduate courses. Prior to each and every lecture, he put in hours of preparation. We could see that. And the lectures reflected that. In addition, he was always available to his students, to a fault. Many times there was a long line of students outside his room, and he made time for every one of them, even if it meant he missed his lunch. Before our annual conference, the American Physics Society Division of Fluid Dynamics, all of his students would take turns practicing and preparing for the talks. There were many, many rehearsals. Mahesh sat through all of these rehearsals, patiently coaching us, talking us through our nerves, enacting where needed, and in the process left us with one of the most valuable gifts: the confidence that we can deliver a technical presentation to a group. And he gave us the tools to do that. This despite our inherent accents, stage fright, or discomfort with public speaking. Personally, I utilize these skills almost every week in my job, and I am very thankful for these lessons. I'll leave you with a couple more personal examples. When my parents visited Minneapolis from India, he invited them into his office. He took time to talk to them. He made them feel I was in good hands, and that was important. 4 years later, when I visited him with our 2-year-old daughter, he welcomed her with a huge smile on his face, took her into his arms, showed her around his office room, and played with her. There was a genuine affection, and it made us so happy that we were back visiting. Years later, I was in a short conversation with him on the telephone. It lasted all of 6 minutes, but he asked me 4 times, 4 different ways. Was I happy with my job, my career? Was I doing okay? Did I need anything? Mahesh continued to care long after I left his research group, and he showed he always had my back. So Mahesh, thank you for everything. Thank you for being so good at what you do. Thank you for being a wonderful example as a researcher, a mentor, a co-worker, a teacher, a professional, and a human being. I am very excited for your new title and this new beginning. Have a wonderful evening. Thank you so much.
Okay, closing in on the main event. So first off, I'd like to echo the Dean's welcome to everyone, to all of you here. Thank you for helping us celebrate this very special occasion. As mentioned, I'm Dave Dowling. I'm the chair of Naval Architecture and Marine Engineering here at the University of Michigan. We are extremely lucky to count Professor Mahesh as one of our NAMI faculty members. He joined the University of Michigan as a professor in August of 2022. Prior to his faculty appointment here, he served for 22 years as a faculty member in the Department of Aerospace Engineering and Mechanics at the University of Minnesota, after completing doctoral and postdoctoral studies at Stanford University. As you may know, hydrodynamic turbulence arises spontaneously in natural flows as the flow speed and the size of the object of interest increase. Thus, turbulence is omnipresent for operating ships, and it causes a variety of unwanted phenomena, such as increased friction, drag, vibration, and noise. Predictions of these phenomena are essential for assessing and understanding the performance of current and future naval and maritime assets. Professor Mahesh's work aligns perfectly with this need. He's the primary developer of computational schemes used by the U.S. Navy to simulate the turbulent flow that occurs in and near ships, submarines, rudders, propellers, and all kinds of other control surfaces. With his recent advances in algorithm development, theoretical analysis, and modeling of turbulent flows, he and his research group can now simulate turbulent flows around and within complicated geometries at extreme off-design conditions, including with bubbles and cavitation, that would have been inconceivable a decade ago. These simulations enable understanding of the intricate details of turbulent and multi-phase flows in a range of real-world maritime and aerospace applications to help engineers design better devices and scientists to make new discoveries too. In my experience, Professor Mahesh is the Navy's go-to guy for simulations of turbulence. When we started a big project recently, we needed CFD done. And everybody said, what is Mahesh going to do? There was no question who were they going to go to. So Mahesh has published over 180 peer-reviewed papers in archival journals and major conferences. He's given more than 75 invited talks and presentations and received numerous prestigious national and international honors, including a Fulbright scholarship in 2018. He's also a fellow of the American Physical Society Division of Fluid Dynamics. So, without further ado, please welcome Professor Krishnan Mahesh for his lecture on simulating turbulence, recipes for chaos.
Thank you, Dave, for the kind introduction. Thank you, Suman, for the kind words and the effort that went into that video. And thank you all for being here today. The title of my talk is Simulating Turbulence, Recipes for Chaos. And what we'll do is to discuss some of our work on simulating multi-physics turbulent flows within the naval context. Before I start, I'd like to thank some people. I'd first like to thank the Couch family for their generosity and support of the college, the NAMI department, and my research. I'd like to thank Dean Gallimore and his team for considering me worthy of this honor. Thank the college and NAMI for their enthusiastic welcome. And I'd like to thank the wonderful students and postdocs whom I've had the privilege of working with over the years. I owe this to them. My road to Michigan is as follows. I obtained my bachelor's in mechanical engineering from the Indian Institute of Technology in Mumbai, India. Master's and PhD degrees in mechanical engineering from Stanford. I was then a research associate at the Center for Turbulence Research at Stanford, and then faculty for several years in the Aerospace Engineering Department at the University of Minnesota. I joined the NAMI in August, toward the end of August, start of this fall semester. On the personal side, this is a picture of my family, my wife Pratibha, kids Abhishek and Anya, all three of whom are here today. So, what is turbulence and why is it challenging to simulate? In a nutshell, Turbulence is challenging because it's three-dimensional unsteady flow with a very wide range of length and time scales. Now, this slide has two pictures. Both are of turbulent jets. One is a turbulent jet from a bathtub. The other is a turbulent jet from an erupting volcano. Now, if we were to stick a velocity probe somewhere inside either one of these jets, we'd see that there are three components of velocity that vary in time. That's three-dimensional unsteady. If one looks at these pictures and one imagines the existence of large billowing eddies, which are of the size of the nozzle diameter for the bathtub and the size of the volcano in the case of the volcano. And alongside these large motions, you have very small motions that depend upon the viscosity of the fluid. That's range of scales. So the range of scales that you have for a volcano is much higher than it is in a bathtub. And why is this a problem? It's a problem because to resolve small motions, we need very high spatial resolution, which we then have to carry over long domains to capture the big motions. To resolve high frequencies, we need small time steps, which we have to carry for long lengths of time to capture the lower frequencies, and that's computational cost. And so there are different levels of approximation. There are different levels of approximation to simulate turbulent flows. One is a brute force approach, direct simulation. You say, I think I know what my governing equations are, I'm just going to compute everything. Well, that's practical for the bathtub jet, but quite impractical for the volcano. And so the engineering prediction of turbulent flows relies on saying, let's just directly compute the mean flow, the time averaged or the ensemble averaged. But there is a cost to be paid, which is that we have to model all the unsteadiness in the flow. There is then an intermediate level. This suggests an intermediate level of prediction, which is to say, let's capture the large motions, the unsteady motions that have most of the energy, and let's model the smaller motions, which may be dynamically less important. Okay? That's called large eddy simulation, and that is the approach that my group has been developing over the last several years. Now, what does this mean in the naval context? Imagine taking a toy submarine and performing experiments on it in this bathtub. Can we take the results from that study, which would be feasible, and apply it to something in the ocean? That's your classical engineering scaling problem, right? So the classical approach is to perform experiments at model scale, in, say, for example, a water tunnel, and then take those results and try and scale them to full scale. For context, the largest water tunnel is an order of magnitude and more smaller than the full-scale application. Furthermore, such scaling, right, which is what we learn, so this Reynolds number, crude number scaling that we learn in hydrodynamics, such scaling is challenging when the physics gets complicated. For example, in cavitating flows, where liquid changes to vapor in regions of low pressure. The physics of cavitation involve nuclei and bubbles at the nano to micron scale to full scale that's at the order of several meters. The scaling is quite challenging. And so the promise of simulations, provided they're accurate enough, is can simulations assist, complement, or replace some of the testing? Can simulations develop improved or, if accurate enough, in some cases, eliminate the need for scaling laws? This is the promise, but this requires that simulations be reliable enough. An overview of my research is as follows. So imagine an underwater vessel like this as it moves to the ocean. The propeller rotates, the control surfaces move, and this vessel interacts with the turbulent flow over it. Now, this turbulent flow is quite complicated. If you imagine flow over this hull, very near the surface, you have highly unsteady, very small motions, whose combined effect produces the resistance that this vessel experiences in the ocean. This turbulence interacts with the control surfaces that are moving, affects their performance. The flow post these appendages then flows into the propeller, influencing its behavior. And downstream of the propeller, the wake has regions of very low pressure where liquid can cavitate, and that produces intense sound. How do we predict all of this? Now, liquid is dense, and so that causes the pressure fluctuations on the surface produce sound. How do we predict things like this? So in our group, that's our core problem. That's what we care about. We are working on problems having to do with propulsors, cavitation, maneuvering, as well as hydroacoustics within this overall context. And why is this important? Because time-averaged approaches, right, which are the current state of the art, are not accurate enough to predict complex physics like these. And so the question we ask is, can large eddy simulation reliably predict these flows? If yes, what do we learn from the validated simulations? The pacing items in this work are as follows. Numerical methods, extremely important to capture turbulence. Turbulence models or subgrid scale models. The physical model, when you have cavitation, what are your governing equations? High performance computing, so our methods and codes use the largest machines in the country. So how do we do that effectively? And the analysis of big data, we generate terabytes and terabytes of data. How do you extract useful information from that? By way of background, our vision several years ago was to be able to compute complex multiphysics flows with a fidelity that was comparable to what we could do canonical flows with. And these two pictures here illustrate what we mean by canonical and complex. On the top, you're looking at, these are contours of velocity in what's called a coaxial combustor geometry. This is the cross-section of a geometry that's basically axisymmetric. It's a canonical configuration to study combustor flows. On the bottom, this is a combustor section from a Pratt & Whitney gas turbine engine. Prior to our work here, this is the most complicated flow that we could do simulations on. And so this work here we went from here to here. So we developed the capability to perform first-time simulations of flow in this real geometry. And a key pacing item, a key advance that enabled that was the development of numerical methods that were robust and accurate without any numerical dissipation on unstructured grids. Okay? Unstructured grids allow geometries like this to be efficiently represented. Not having dissipation is important for turbulent flows because you don't want to kill the smaller eddies that are dynamically important. But if you don't have dissipation, codes are unstable. And so that was the core sort of technical challenge that allowed us to go from here to here. Our in-house solver, we just call it MP Kugels, since then has been extended in terms of its physics to go from incompressible to compressible to multi-phase flows. In addition to this, in our group, what do we do in our group? We also develop turbulence models from the perspective that we'd rather not have any adjustable constants. Okay. Our group performs and analyzes results from massively parallel simulations. We use the largest machines in the country. And simulations are to be viewed with a certain level of skepticism. And so we are constantly interested in theories that allow us to anticipate and predict the errors that such simulations have. This capability has evolved over the years, and I thought I'd share with you something that I'm very excited about, something that we've developed over the last 3-4 years and are now actively pursuing. And this picture here sort of illustrates what it's about. So here, the contours here show you velocity in a turbulent channel. 2 plates flow between them. Now, if you look closely, you see little specks, yes? Now, if you zoom into this region, this is the volume. You see each of those specks is actually a particle. And if you zoom into each particle, you see that the flow around it is resolved by that computational grid. So what's going on here is that you have hundreds of thousands of grids resolving the flow around these particles, moving in a very unsteady manner and talking to each other. The core challenges there are addressing conservation properties and parallel scaling, and these 2 papers address that problem. So what we'd like to do is to take capability like this and apply it to take us toward that moving body. We'll now look at some applications of this capability. This slide is an introduction to what's called propeller crashback. So propeller crashback is an extreme operating condition where the vessel moves in the forward direction, but the propeller rotates in reverse. Okay? This is an emergency sort of operation, and it's a very critical sort of constraint on the design. This movie here is from experiments performed at the Warfare Center at Carderock that show you the flow around a propeller that's in the crashback mode of operation. And what I draw your attention to is this highly unsteady flow in the vicinity of the propeller, whose size is of the order of the propeller diameter. Now, the reason crashback is important is that it results in highly unsteady thrust and torque, which affect propulsor performance. Now, the transient loads can be high enough to cause blades to damage. Okay? So boats come back from fleet trials with damaged blades in the crashback mode of operation. And when you have highly unsteady forces, that impairs your maneuverability. And the reason we got drawn into this was that state-of-the-art RANS codes, which work very nicely in steady forward motion, failed to predict even the unsteady loads in crashback. And because the flow is massively separated and unsteady, the question posed to us was, can your unsteady methods predict crashback? And this was our roadmap toward the problem. We first looked at basically an open propeller. Open propeller means you have a shaft, a propeller, no duct. And we looked at simulations under the same conditions as experiments performed at Carter Rock. This paper has all the details. And what we found is that our simulations were able to predict not just the magnitude, the mean value, but the RMS, the spectra of the loads, and also the velocity field, velocity profiles in the vicinity of the propeller. And these validated simulations were then able to predict the reason for the unsteadiness in the loads. And here is the essence of what we found. If you take a propeller blade, the cross-section of the blade is an airfoil. And so when the propeller spins in reverse, it's like flying that airfoil at a negative angle of attack. So your pressure and suction sides switch direction. And so what your entire propeller disc is doing is pushing fluid in the upstream direction, where it interacts with the free stream flow. When two streams of fluid interact, they produce a vortex ring. And at these Reynolds numbers, under these conditions, that vortex ring is unsteady. It's unstable. So anytime that ring breaks and sheds, free stream fluid accelerates to occupy that region. Associated with that acceleration is a pressure gradient, which means if this is your propeller disc, you now have transverse forces, which are your side forces. Yeah. And so that is an example of insight made possible by these unsteady simulations. We then looked at another experimental observation, which was that when they attached this propeller to a stern, under certain conditions, under certain rotation rates, the forces went up, the side forces went up. So we performed simulations, we were able to reproduce that behavior and explain it. And here is the essence of what we found there. So if my fist here is the stern, okay, and this is the propeller, right? Now what the propeller is doing is pushing fluid upstream. Yeah? If the stern were in there, this basically fluid interacts with the free stream velocity to do what we described earlier. If you have a stern, this upstream flow impinges on the stern and causes a recirculation region. And so effectively what that does is reduce the average velocity of the free stream toward the propeller. So that vortex ring is now a lot closer to the disk and affects it more in that flow regime. Okay? And this insight was made possible by the validated simulations. Modern propellers are ducted. Okay? And experiments found that for ducted propellers in crashback, the side forces go up a lot in the presence of the duct. And so we looked at that problem. And this movie here is an animation from our simulations, the flow around crashback around a ducted propulsor, again under the same conditions as experiment with which we agreed. And here what you see, what you're visualizing is the vortex ring. It's unsteady, and when you have a duct, you see that it forms outside the propeller duct. Okay. Now, in addition, do you see inside the duct, do you see these regions of sort of intense activity? That's the tip gap. If I have a duct and a propeller rotating like this, there's a small gap there. And in crashback, you have separated flow even inside the duct near that tip gap. And so the bottom line is when you have a propeller inside a duct in crashback, you have a highly unsteady pressure field on the inside. So your side forces go up a lot due to the forces acting on the duct. And this behavior was consistent with the experiments. And I just wanted to show you one example of why, of the kind of what we do when we do these computations. Okay? The details of the curves aren't important. What's important is that we are comparing our simulations to experiment, okay, for the mean axial velocity and the mean radial velocity at 9 stations. That's really what these curves show. And the agreement is reasonable. So this sort of comparison is what we aspire to and what gives us confidence in the conclusions that we draw from these simulations. This slide has a couple of examples of other phenomena that propeller flows display. On the top, you now have a propeller in the normal mode of operation. You're looking here at contours of velocity. Red means high, green is low. And so what you're seeing is the slipstream. The flow is being accelerated through the propeller disc. Okay, this blue region here is what's called the hub vortex. Now, if you look a little closely at these, at this movie, what do you see in the near field? You see these little blue regions here? That's the tip vortex that's being shed by the propeller. And then near the propeller disc, you see the flow is somewhat coherent, right? It gets strained because of the gradient in velocity here, and then downstream it's sort of chaotic. So we looked at all of this, compared our results to experiment, and used the results to propose a mechanism for the wake instability. And the reason this is important is that these vortical interactions downstream of the propeller blade are what cause cavitation inception, tip vortex cavitation downstream of the propeller. Now, a propeller or any body that moves in water produces sound. Okay? Now, when you have water, the dominant source of sound are the pressure fluctuations on that body. Now, here we are performing three-dimensional unsteady volumetric simulations, which means we have that unsteady pressure field. And so what we can do is to use that unsteady pressure field to analytically propagate that sound to the far field. It's called acoustic analogy method of predicting sound. And that's what we did here. The details are described in these two papers. And this is a visualization of this picture is not to scale. Okay, this sound is at several hundreds of propeller diameters in the far field, but we can basically use simulations like these to predict far field sound at these very low Mach numbers that flow in water corresponds to. And since we have volumetric data, we have the entire flow field, we can answer questions like these, right? You look at acoustic spectra in the far field and then say, what are the hydrodynamic sources of sound? Yeah? And this paper has details on that. This slide describes some of our simulations on flow over a hull. So what you have here is what you have here are results from a calculation at a Reynolds number. Okay, think of Reynolds number as scale. The volcano is very large Reynolds number. The bathtub jet is a low Reynolds number. And so this is at a Reynolds number based on length of around 1 million. Yeah, and what this picture here visualizes are the very small vortical structures near the surface. Okay. Now we've all heard resistance, yeah, or drag when something moves through the water. Now when the flow, that's one number. Now when you look at the flow, the turbulent flow in the vicinity of the hull, in reality it's highly turbulent, highly unsteady. And each of these structures like these near the surface are what graze against it and integrate to produce drag. So resolving them becomes very important. You see the sail and you see the appendages here. Now you see this region here that looks like a sort of a ring. What it is that experiments at model scale use what's called a tripwire, okay, to take laminar flow and make it turbulent to get behavior that's more representative of what happens at full scale. And our simulation capability allows us to directly resolve the tripwire in our calculations. That's the only point these two figures here make. Okay? And when we do that, the results that we get agree with experiment. I'm here showing you the pressure on this body. This is the leading edge. This is the head. This is the tail. Okay, of this body here. Symbols are experiments. We are the straight lines, and such is the agreement. And then we used these results to basically look at the flow. And there is an approach that we like now that's based on streamline coordinates, which allows basically different regimes and different to be analyzed using the same framework. And furthermore, these simulations reveal the importance of accounting for transition on the scale, on the sail, okay, which is much smaller than the entire body. And these papers here describe those details. Now, 1 million seems like a lot, but something in the ocean is of the order of 100 million. And so this work is continuing in terms of developing models for this near wall flow. A prolate spheroid is basically an ellipse that's rotated, so it's a body of revolution. It's a canonical geometry that models more complicated hulls. This picture here is a result from a calculation of flow over a prolate spheroid at a Reynolds number based on length of around 4 million. Okay? And the things I want to draw your attention to are, first you see this region here that looks like a ring, except it's not. It's basically 238 posts that were used in the experiment that we are modeling here. And we basically resolve the geometry of each of these posts like so. Okay. What is animated here on the body are contours of skin friction. So think of it as velocity very near the surface. So where it's white, you have large velocity and the flow is kind of turbulent. Where it's gray, the levels are low, the flow is relatively more quiescent. And what you see is how just downstream of these strips, right, the flow becomes turbulent. Then you see how there is cross flow in that this body is at angle of attack, okay? So you see how flow goes from what I'll call the windward side to the leeward side, like so. On the top of this body, you see there's a lot of white. The flow there is turbulent. On the bottom, it's relatively more quiescent. Okay. Now, there is an ongoing project. The reason I wanted to show this is that there is an ongoing project called the HYPRO project, right? Which involves, it's a multi-institution project with Dave Dowling and Steve Cessio involved in the experiments here at Michigan, and we are working on the computations. And there are these similar experiments being done in the largest water tunnel in the US, okay? And we are very interested in what happens to flow over this at high Reynolds numbers. And one of the things LES, our simulations are able to do was to basically inform the design of these experiments as they are being planned. And simulations like these basically offer, and I'll support that in the next slide, considerable insight into the complicated flow on this body. These simulations reveal the importance of laminar to turbulent transition even at high Reynolds numbers when you're yawing or pitching. Okay? And the considerable effects of curvature. If you look at this body, you take an ellipse and rotate it, you have curvature in two directions. And that has a huge effect on how the flow on this body evolves. And so these observations have resulted in more fundamental work as part of NATO AVT groups and other efforts at ONR. These details are described here in this paper. And I wanted to show you this one picture that illustrates the considerable complexity of the flow on the body as revealed by these simulations. And this is very hard to get otherwise. We'll walk our way through. The slide seems a bit busy. Again, what we are animating is skin friction. Just think of it as velocity very near the surface. Phi and x over L. What we are doing here is taking that ellipse and unwrapping it. Okay? So x over L of 0 is the head, L is 1 is the tail. Phi of 0 is the bottom, phi of 180 is the top, okay, of that ellipse in which we've unraveled. Okay. Again, this line here, those are those 238 posts. Here is the turbulence that's being generated, and then you see this is a cross flow. It goes from the windward side. Instead of just going downstream, it goes from the windward to the leeward side. Do you see how these regions here, they have more black in them? And instead of having intense turbulence like this, they have what look like disturbances, right? With some finite wavelength that are propagating from the windward to the leeward side. You see how this flow on the leeward side has the highly turbulent flows, a region that is separated from relatively quiescent regions. And so you have turbulent diffusion occurring there. That's what we call regime interface. You see this region here where streamlines appear to converge. That's where this flow separates to form big vortices that affect the loads on this body. And lastly, do you see how here turbulent flow, near the top, turbulent flow becomes more quiescent. On the bottom, quiescent flow becomes more turbulent. This has to do with pressure gradients there. So this is a level of complexity on this body that is made possible by calculations like these. And this is why it's challenging for time average models to predict. So one of the things we're doing going forward is to see how this can inform the development of the simpler models that we would like to use. Okay, we study cavitation, which is a transformation of liquid to vapor in regions of low pressure. So why is cavitation important? So cavitation is important because it increases noise. It's very noisy, and when it's large, can cause material damage. And this is cavitation noise. Okay, this is a movie provided by our colleagues in Tasmania, and this is real sound. Okay, this is a hydrofoil here. You're looking at a top view. This is a vortex behind that foil that's cavitating, and when it cavitates, this is what you hear. So imagine this happening under the ocean. If you cavitate, everyone knows you're there. So cavitation matters. If the cavitation is large, okay, this is what happens to metal. This is erosion of a rudder, okay, due to cavitation. And so how do we simulate cavitation? That's our core question. Okay? And for context, we made a lot of progress on this question in a recent ONR MURI that will end this year that involved 8 institutions and about 25 students and postdocs. So this slide shows you simulations of cavitation. Can we predict it? That was a question asked here. Under regimes that are relevant to erosion. These simulations are performed under the same conditions as experiments done by Steve Cessio here at Michigan. And the novel thing about their experiments were that they use X-rays to actually get numbers for vapor volume fraction. Okay? And so if you look at this picture here, what it shows is cavitation behind a wedge. So the flow is in this direction. Pressure is low at the apex of the wedge, and the white region here it basically shows you vapor. So there's a sheet of vapor that forms, it rolls up into a cloud, and that cloud collapses in the high pressure region here. Okay? Anytime vapor forms or collapses, there's volume change. So it's highly compressible. And that produces very strong pressure waves that are visualized in this vertical plane here. So a cavitating flow is a very violent and sort of intense flow. And so here in the calculations, we had to model cavitation, which we did as a compressible mixture. And we developed numerics to solve that system. And next, I draw your attention to how well do we agree with experiment? So what these pictures show you are basically profiles. This is the wall, this is the free stream of vapor volume fraction compared here at 5 stations to experiment. And such is the agreement that we obtained. Another reason I wanted to share this with you is that this flow, we tend to think of water as being incompressible. But when it cavitates like this, the flow is actually supersonic. Because when you have vapor, your sound speed drops from 1400 meters a second to something like 10 meters a second. So your Mach numbers now are very high. And the experiments showed that basically what causes this cycle of cloud formation and collapse is the propagation upstream of these supersonic bubbly shocks. The simulations were able to reproduce that behavior qualitatively as well as quantitatively. Cavitation is very rich from a physical standpoint, and these are some of the things that we are currently engaged in modeling. Water has not just vapor in it, which is related to liquid by thermodynamics, it also has dissolved gas, and the two are different. Dissolved gas is non-condensable, it has finite compressibility. Vapor has very low compressibility. All right? And so how do we model that difference? How do you predict cavitation inception, which basically involves very small nuclei? Think of them as defects in a liquid or small pockets of vapor or gas. They're being transported in this turbulent flow, being entrained within the cores of very tiny vortices where they grow. And when they grow explosively, we call that inception. That's what produces that intense sound. Can we model it? This paper discusses that. And this here is an animation. You see this little blue region that pops up in this very turbulent flow? Those are regions where the pressure is equal to vapor pressure. That's where it should cavitate. Right? And you see that it's very instantaneous, intermittent, and it actually happens in these very tiny vortices. And one of the things that the simulations revealed is that it's vortices whose rotation rate is 4 times the strain rate, okay, that this seems to occur. Now, if that's a general statement, then that can be the basis for Reynolds number scaling that we started the talk with. Now, cavitation is fundamentally multi-scale in that you can have large regions of vapor along with very small bubbles that you cannot resolve on a grid. So can you develop a computational capability that simultaneously can resolve this and this? And we've developed the initial stages of such an approach described here. Now, nuclei, cavitation starts from nuclei, which basically is modeled empirically. We assume its existence. But is there a theoretical way to predict nuclei levels? And we've developed an approach in this paper that's quite different from, it's not a CFD-based approach. It involves the minimization of Gibbs free energy. And one of the things it has done is it's allowed us to predict trends of nuclei data collected over 60 years by our colleagues in Australia, from the ocean to their water tunnel. And one very interesting thing they show is how their slopes are -4, and we get that behavior using this model, and we can explain why. Okay, so these are some of the things that we look at there. So this one slide kind of captures sort of the broader impact of this sort of a work. These bullets here were provided to me by Dr. Peter Chang at the Office of Naval Research. Basically, our code is being continuously transitioned to the Warfare Center at Carderock, who've performed validation studies for fleet propellers. They apply to other things, and they've certified the use of this code in their simulations and established confidence in its use. For example, the code was transitioned into the Ohio replacement program several years ago and has been applied to a range of other problems and programs there at Carderock. And this one slide, I just wanted to share it with you, is a slide given by the Director of Transition at ONR some years ago. And it says, FNC products leverage basic research to develop mature products. Okay, and so this is basic research, this is acquisition, and you see this thing here. This is a simulation of propeller crash back at Carderock using MP Kugels. The physics of these naval flows are very rich and general enough to apply to regimes and disciplines other than these naval problems. And I wanted to share with you one example to make that point. So this shows you simulations of basically a Mach 1 jet. This is air now. Okay, of a Mach 1 jet in a Mach 1.6 cross flow. So this image is basically, this image is showing you the flow in two planes. One is horizontal, one is perpendicular, of density gradient. Okay, so you have a jet and a free stream. And why is that important? Because that's what happens inside scramjet engines, okay, where fuel is injected into supersonic cross flow to cause it to burn. And if you look at the complexity of this flow, which is performed under the same conditions as experiment, you basically see that there is a turbulent boundary layer from upstream. As this jet comes out, the supersonic flow sees it as an obstacle, forms a shock wave, right? The boundary layers, the pressure goes up across the shock, right? And so this boundary layer wants to separate. As it starts to separate, it makes these compression waves, which merge with the shock, right? Then the shock itself, the jet as it comes out, is what's called unadapted. The exit pressure makes the formation of these shocks here, barrel, called, for example, the barrel shock being one example in this Mach disk, and the whole thing is unsteady. When shock waves interact, you produce vortices, and so the downstream flow has these coherent vortices along with fine-grained turbulence. This is the level of complexity that we attempt to capture in these simulations, which also in this paper are compared to experiment, which we then attempt to explain. This is another application of a problem like this. Here, this is called for control. Now you have external flow that's subsonic and a jet that's supersonic. Here we looked at a problem that Sandia had looked at. Okay, again compared to them and explained the flow. But the main point I wanted to make is how the physics and the science in these NAMI flows are broad with application to other disciplines too. And this is my concluding side with sort of my sense of future developments. Okay. About 20 years ago, we went from vector machines to parallel machines, and that kind of changed what we could do. There's a similar trend right now over the last 5 years, 10 years, it's been gaining steam to where hybrid use of CPU and GPUs are going to enable at least an order of magnitude, some cases 20 to 30 times in simulations like these. What that will do is things that we could run, or we right now run on big machines, would be possible, things in the 100 million kind of range, on much smaller machines. That will bring unsteady simulations like these more and more into the design realm. And what we can do on really big machines is to approach those model scale experiments more and more closely. Multiphysics, big computers alone are not enough. The physics here is quite complex and quite rich. So things like surface roughness, transition, cavitation, fluid structure interaction, hydroacoustics, and so on, research into them will continue. Now, a lot of things that we showed here have to do with stationary bodies. When things move, you add an entire new dimension, which opens up entirely new class of problems. Okay? Numerics and turbulence models continue to remain important. How do we make sense of big data? We generate terabytes and terabytes of data. How do we reduce that to things that are more useful, right? And not just a profile somewhere. Assimilation. We now have, you may have a simulation of something, you may have an experiment on something. Is it possible to intelligently combine that data? You may have different types of data from different sets of experiments. Can we combine all of that into some sort of predictive approach? And to make that case, this is an example of a project that we are working on right now, where we're working with particle tracking velocimetry. So you have particles in a flow, and they're trying to develop a measurement technique that we are combining with our numerical approaches to kind of provide a more informed sort of prediction of things. And lastly, the physics that we are after is multiphysics, is quite varied. And so both our capability can enable and be enabled by multidisciplinary interactions. An example of which is an effort that we just recently proposed on metamaterials interacting with flow. And then there are several other possibilities, biofouling and icy flows, where experts on how things grow, how to model them, the thermophysics of ice, its mechanical properties can help us. Cavitation is not just noise and erosion. There are applications, water purification and medical applications, which we might inform. What we do for propellers can be applied to wind turbines and offshore turbines. We talked about, right now the focus is on exascale machines, but then there's quantum computing on the horizon, for which CFD is a very useful use case. So there is a natural collaboration there. And we said develop simpler models on big data. Machine learning, which is gaining more and more traction in the last 5-10 years, can inform us. Experts in that field can inform us. So the bottom, and so my concluding remark would be, I think that the future of both looking at the science in the NAMI discipline and its interaction with a broader section of the university community is very bright, and I look forward to such interaction during my tenure here. And that concludes my talk. Thank you for your
So, that was terrific. We have time for questions first. So, who would like to ask questions?
Thank you.
So Mahesh, you worked in Turbulence for 30 years now, right? Or close to that. With all these simulations, are we learning new things, new theories that go beyond what we knew from the 1950s and 60s, from Kolmogorov and others? Or those are valid still and we don't have to adjust them?
Well, when you say theories, that's sort of what exactly do you have in mind?
In terms of scaling relations, for instance, for turbulence in these kinds of flows, are we looking at new scaling laws when it's more complex geometries, or that's not the path to pursue? Like it's more towards.
I'll give you one example. Take propulsor cavitation. Okay. So there are classic scalings that go from model scale inception. It's inception. Scalings that take you from model scale to scale. Now, when you look at the flow in a ducted propulsor, and there are physical arguments for that scale. Now, when you look at the flow behind a ducted propulsor, the wake, the downstream region is dominated by interaction between that dip vortex and something that happens in the plate wake. And the classical scalings, such as one experimentally and then it's built more closely, those classical scalings, they did not work, as found by Carter. Question is why? The basic physics is vertical interaction. And so there's been study experimentally, now computationally, that looks at this. Now, when you compute this flow, what you see is that describing it as two coherent vortices interacting is also simplistic. Okay? The blade is continuously shedding vorticity at different scales of interaction. And that is affecting what is happening. Okay? So I'll give that to you as one example. If you take, and there are others.
Very nice talk, Mahesh. You mentioned, one numerical property of interest is low dissipation, handle turbulence. When you have compressible flows and shocks, often people seek out high-order methods to try to resolve these really small structures. What sort of philosophy do you take? Are most of these simulations on the order of second order, and you just use low dissipative schemes with a lot of resolution, or are you exploring high-order methods too?
Okay, so I think it's a two-part question. Yeah. So in terms of shocks, what we do is to do a lot of shock people who do shocks come from the shock capturing world, where you say I have to be intrinsically dissipated, and then they say I'll dial down the dissipation. And going high order is one way to do that. We've approached the compressible world in the opposite direction, which is to say we want non-dissipative schemes for the turbulence, but shock capturing has to be dissipative in order to, very locally. And so we do it locally. And so we use a predictor-corrector approach, where the predictor step-us of the properties we like, and then the shock capturing is applied locally. And we use a method called characteristic filtering to do that. Now, do we do low order or high order? These simulations, as the geometries get, I would say both. Okay? The geometries that you saw, your second order for free. But recently, actually, it's under review, we've developed a method. It's a hybridized method for tetrahedral elements that's actually arbitrary order. And we've seen some very promising results. So going forward, that certainly is on the table in terms of a direction that we want to go.
Yeah, most of all what you talked about was deeply submerged flows. And I'm wondering, have you looked at all the free surfaces and what effects? In other words, submarines are one thing when they get near the surface or when you have normal ships.
Right.
Things change, I think, but I don't know. That's what I'm asking. What do you see as
We have looked at free surface flows, not to this level of detail. We've studied free surface flows within the context of superhydrophobic surfaces, where you have a surface and then you have some gas trapped and then you have an interface with liquid. We've studied it in that context. We've looked at free surface flows in the context of cavitation, where you may have a large cavity that forms near a surface, is responsible for keeping the cavitation going. We have not studied surface ships the way, say, Kevin has studied, the way there are a couple of problems for submerged bodies that involves free surfaces that we're interested in and are tacking towards, and it has to do with near surface operations, where proximity to the surface, you can be submerged, but close to the surface, and it still affects your dynamics. So one of the directions that we intend to go in is taking what we can do for these sort of cavitation-free surfaces or super hydrophobic surfaces and applying the problems like that. And the key challenge there is developing a free surface methodology on these sorts of complex grids. We like this volume of fluid approach because it's conservative, but extending it to complicated grids is not. So that's where we stand.
Yeah, and then you.
Great presentation. So you kind of touched that in the penultimate slide of your presentation, but can you give us some specifics of, say, 10, 15, 20 years from now? Where are all these things going? Some specific examples. You talked about what you want to bring in terms of tools. What is it going to enable in 15 years?
So if you take a certain class of problems, let's take crashback, since I spent some time on it. So crashback, when it started, we started say about 10, 12 years ago, when we started working on it. The motivation was that it mattered, but potential codes and range codes and so on could not predict. We could. But the calculations still, the first time we did it, were very expensive. And so, but it was still adopted. And what they did was to run it on smaller grids. And then say, although my grid is small, I'm still a lot closer, I'm getting all the unsteadiness and I can use it. And it ran on a big machine. But the results were obtained within a time frame that was reasonable. Now those machines have gotten faster. The codes have gotten more sophisticated, right, in terms of complexity. We can do real propellers, and we applied it to propellers like that. Now you go GPU. If I gave you some numbers, I think that, in fact, the GPU effort that we did here, we ran something like a 20 million problem on a small desktop. That's how we developed the method. Okay, so we think that once the CPU-GPU acceleration will enable calculations in the order of 80 million, 100 million, these sorts of ideas to be done on small machines. And so the paradigm will change, and this is what actually we are trying to encourage people to do, in that a group, whether it's a group like ours or a Navy group, can basically think of each engineer can have access to a node or two of a GPU machine. All right, that they can just run problems of that scale continuously, and you go to the big centers only for things that are even bigger. So I really feel, and then there is the physics, right? As things get more affordable, an engineer tends to ask for only what they can get, constrained by what their needs are. Right? And so they went to the cashback world. They're willing to pay the price because the implication is safety, not efficiency. Yeah. So you're willing to pay the price. So now, likewise, when it comes to sound, that's a huge thing in terms of step. So you pay the price. And so I see, acoustics, cavitation, inception. Inception and erosion are kind of cyclical in terms of priorities, right? I see for problems like that where if a method like this works, it's easier to use. If it's affordable, you will use it. So I definitely think in this world, in the context of what I discussed, I see things like this becoming more and more applicable. And these sort of assimilation things, I didn't mention it. How do you combine a time average result with an experimental result and a few LES results? Like how do you combine local experimental results with a global LES? That's how things, I see that trend, and it's starting.
First of all, congratulations for a great presentation. You mentioned chaos on the title of your presentation. I'm wondering, since you have all the data, if you had any chance to quantify, characterize the chaos that is caused by these motions.
It depends on what your choice or what you mean by characterizing the chaos is.
For example, you can take just a few trajectories of particles calculate the characteristic Lyapunov exponents, find the
Exactly.
dimension of the space.
Yes, that's it. So we have not done that. We tend, that's what I was asking. What we tend to look at in these applications is really the unsteadiness of the flow, not so much in things in terms of Lyapunov exponents and the dimensionality and so on. That sort of, when we have particles or bubbles and so on, then we look at their kind of deviation and things like that in the context of do they encounter low pressure regions, but not in that sense of fundamental chaos studies. I would probably want to go to a DNS where you resolve a lot of those motions instead of even modeling. Probably wouldn't want to model the smaller scales even for such characterization.
This may be a route to find some more.
That's an interesting thought, definitely, for sure.
Okay, any other questions? Sure.
Thank you.
Come to my article questions. So these professorships, they recognize not only the science but also the person who does the science. So if you could go back to your PhD, would you redo all of this or would you take a different path?
When you say redo all of this, what do you mean?
So knowing what you know now, would you have taken a different path?
Post PhD.
Or any time of
And I'll amend it before the bank in Silicon Valley.
Yeah. Probably. I would say I was not sure about, if you ask me the end of my undergrad, why did I do CIP? I didn't have a good answer. In fact, my bachelor's thesis was experimental. And I knew that I wouldn't be very good at it. So I said, oh, CIP looks interesting, we'll do it. And that group there was good, I just did it. Toward the end, when I was working, I spent 4 years working on that combustion thing, and nothing was working. 4 years was spent on just dumping code, nothing was working. And as you know, when you're developing a code, if you don't have results, you have nothing to show. You can stand up at a review meeting, and what do you say? And that was 3-4 years of my life. At that point, I did question. Because that period also coincided with a huge boom in Silicon Valley. A huge boom. And so you had people who just get together tea and they were talking about these, folks who, by then I was in the country for my PhD, I just started, I was 8-9 years. I was driving a beat up car and people who had come 2-3 years ago were buying homes. And I still remember, we visited a friend of my wife's and, we pulled up in her car and he had this home with a swimming pool and this European garden. I'm not kidding you. And he actually asked me, so, why are you doing a PhD? I don't quite understand. I said, I just like you. That's why, maybe I drank the Kool-Aid, I don't know. But there was that phase, a brief phase of like a few months where I did question, whether I was just doing this just for inertia. But I kind of liked it. I liked the environment. I liked interacting with the people at the university and so on and so forth. And I still do. And so that's, I think, the best part of our jobs. Just constantly, because even if I can't do something or come up with something new, some student does. A student does or a colleague does or something. And I think that's a wonderful part of our jobs that I really like and cherish. And that's what I think keeps me going.
Thanks, Mahesh.
All right, that seems like a pretty good note to end on. So let's thank our speaker again.
Thank you.
All right, so I have the pleasure of presenting you with 2 mementos. The first is your medal, which I get to put on you. Very exciting.
Thank you.
And then next is your chair. Yes, you can share. Actually, you're a chair. Here's your chair.
Oh, thank you. Thank you.
So once you do a test drive.
All right.
Well, congratulations again. Great. So this concludes our program. The reception is
In the back, please, and we'll take some pictures, and please stick around and congratulate our.
Thanks for coming. No, not necessarily. That's okay.
Yeah, that sounds great.
Okay, let me test it. It's a little bit
Yeah, so when it's like, that you would like to